my research group is for the project. We're not going to have music or anything like that. But this logo is created by my student. The idea behind this project symphony is just like exactly what you would imagine. What's a symphony like? You have a violin player, a cello player, someone who once in a while plays drum. You need everyone else to hear the wonderful sound and harmony. Each one of them will achieve even more when they work together. So the idea of a project symphony came from that fundamental concept that we appreciate. My research deals with broadly that soft interface chemistry. When I was doing PhD under my professor, Manager Hall, it was nothing but soft, right? It was a hard surface interface, and that surface chemistry is something that I inherited under the professor, and particularly actually. Usually I don't give a talk in front of my professors, so right now I'm super nervous. My PhD advisor is staring at me, so I'm a little nervous. So, if I'm not doing a good job, and it's present. So, I will talk about a little bit about the project symphony portion of it. However, I'm going to spend, although I know this is not a research seminar, so I'm not going to go into too much of detail about my research. However, bringing that has some connection to it, so I'm going to spend no more than 5 or 7 minutes to talk about my research to give you the taste of what it is like, so that you will appreciate what my students do under that kind of research agenda. So in general, I'm interested in soft materials and living systems that include membrane, pretty much a major component of our cell is made of. So how those membranes will be able to keep things in and out through the special structural arrangement. Those are things interest me. So we study that kind of concept. Not only that, I'm also intrigued by the idea of soft controls and in biological systems, there are so many functional materials such as teeth and bones and things like that. And those are good functional material. And if you happen to have a kidney stone, that is not so ideal functional material, but you need to know how it forms. Those hard, remarkable hard material is actually controlled by soft underneath template. So we call that as a biomineralization. So in order to study those things, you actually need to know about membrane arrangement and the presence of protein and things of that nature, how it triggers and enhances or prohibits such crystallization. So those are the overall topic. In order to study those things, I chose to pick the system that we can study through microscope. So in general, I use micron-sized droplet. I am going to use the word droplet frequently. If you paid attention in the very first slide when I talked about Project Symphony, underneath the group website is called dropletbylayer.com. That's the domain name I purchased. So we use that as our signature. So this size of the droplet is held by micropipette, and as you can clearly see, this is a hair of one of my students, so that I can kind of compare what kind of size I'm talking about. So about 50 micrometer diameter of droplet. And when you work with this small size, you can easily see the surface area to volume ratio is large. As a result of that, a lot of advantage coming in, including heat transfer, fast kinetics, and things like that. So something that might take a long time, you will be able to see it just like that. And that's the reason I use all these small size container as my test tube. So to do those things, the major equipment I have is not like the traditional chemistry lab. As you see, it's one fraction of my laboratory. As you see over here is inverted microscope. It's more like a biology laboratory, another one of those inverted microscopes. Once you carefully look at the station, within that you will be able to see micropipettes set up. Obviously, we are dealing with the micron-sized objects, so our macroscopic hand is a little too hard to deal with it. So therefore, we need some tool to handle those micro-sized droplets. So that's what this micropipette is about. Those micropipettes are designed to create and hold and then manipulate from there on to study what I described earlier. So you will be able to see those stations as well. And in addition to do that, sometimes looking at something is powerful, but also as a chemist, that's not really satisfying. We are not into violence, we're not looking at things. I want to know what those are. So we need to know the chemical makeup of those. So this is a focal Raman micrometer connected to micro pipette. So therefore, once you have those micro-sized droplets, you purposely created it, and then you will be able to analyze what those are. So if those are the two, what kind of things we study? Each one of them is actually you're looking at water droplets submerged in an oil. Oil contains lipid, phospholipid, or it could be a surfactant, anything that forms a monomer around it, as long as there is an amphiphilic property. And when you bring two of them together, you can imagine right in the middle, it forms a bilayer. Therefore, the name droplet interface bilayer, for that is a DIP. And that's the origin of my website called dropletbilayer.com. Is basically that. If you carefully look at in the middle of that, you can think of one side, my finger is a hydrocarbon tail or AC tail of the compound. Another tail is there, two of them come together right in the middle, making a bilayer that's like a zipper. So right in the middle is the simplified section of biological membrane, phospholipid membrane. So I use this central area that I artificially created to mimic the biological membrane. By modifying the concentration of left and right, I can induce osmotic water transfer, for example. And how fast the water is moving from one side to another will tell you what kind of a membrane it is. Because the property of a membrane, depending on the composition of such, and depending on the composition, it will let water easily move from one place to another. So you can easily monitor by looking at the size change. You can correlate to the volume change of size is related to the area through which water moving, and as well as concentration gradient. At the end, you can get permeability coefficient. Not only water is moving, small molecule, even fluorescein is moving. You can follow fluorescence microscopy, be able to measure and quantify it, and you can run things like that. Without going too much of detail, the point I'm trying to make is that by measuring those water permeability through the water droplet, you can actually relate to structure of a biological membrane. So these are a few examples that shows that depending on what kind of composition that membrane is made of, the permeability can be different twice. More permeable for a membrane that contains one more double bond. So power of a double bond to make membrane more more permeable and things like that nature. As you see it underneath, there is a citation for the paper, and all of them are the graduates. They are the co-author of this paper, and they are the main experimenters for the experiment. Not only that, membrane can be considered as a parallel capacitor, so you can measure and calculate capacitance between them. The capacitance will tell you the thickness of the membrane. So things that you learn in biology, the 5 nanometer thickness, you can actually measure that. Depending on what's in there, what else is in there, what else is not there, change the thickness of them, so electrical properties measured. All of this that I'm describing very briefly is undertaken by undergraduate students. As I mentioned, one of the aspects that I'm fascinated by is the ability for soft surface to be able to control hard material that is soft templating, inducing any kind of crystallization, including biomineralization. So within the same concept of that I described, the small size microdroplet, and once again contains surfactant or any kind of potentially capable of guiding crystallization is surrounded by it, and then within that is crystallizable solute, including protein. And then as this dehydration occurs due to the solubility between water and oil, and with the help of surfactant monolayer, it creates unique crystals. So we were very successful for doing this kind of research to be able to controlling polymorph or destroying certain perfectly working template, but simply changing ions, and you can disrupt that kind of a soft template, truly demonstrating soft. I don't know what it is. I love that concept. Soft. So these are just a flavor of research I just quickly show you. Now that I extended that research, I just have, since last year I established with Shoji Takeuchi, who actually recently got an ACS award in analytical chemistry. So I'm working with him. His lab has a lot more toys than I have, and that's one advantage. And then he has a multi-scale microfluidic system, so I'm sending students to Tokyo every year. So that's the expect of that. I was, during the talk, I was talking, I think just here, briefly mentioned that when you have a role as a professor in PUI, you don't consider research and education as two separate things. You don't consider research and teaching as a separate thing, then you will never be able to achieve either one of those because you simply do not have time. You will be asked to teach 9-9 or 12-12. In my institution, 12-12 is what you have to teach. 12 credit means every semester 4 classes you have to teach every semester. And when do you do research? You have to find a way. Your research is your teaching. Your teaching is your research. There is always a way that you can find it. There is no way that, oh no, my research is so high level, I cannot possibly imagine using this in education setting. Or I think you did not think hard enough if that's the case. As long as they have a general chemistry concept, you can educate them. And I will show you how I built those systems. So this is a true example of that. I didn't just set out to do these things, we made it to the cover of General Chemical Education. These chemical reactions, while we were doing all these experiments that you just briefly heard about droplets coming together, we discovered, oh, this is neat, it's full. Actually, can we do this experiment just for the fun of it? We finished this series. Can I just put this thing, see what happens? And all started with the enthusiasm of the students, but we didn't start with the education per se. We didn't want to, let's write some pedagogy paper. Didn't start with that way. We started doing our research and then come up with all these new things. I was able to show some of those, oxidation reduction reaction is really cool if you demonstrate it under, 50 micrometer diameter. Some of the chemical reactions just happen immediately when you have 100 milliliters each. Mix it together. What just happened? Okay, change the color. That's it. You can just stop and rewind the tape to fragmented to analyze what happened. But you can, if you videotape that micron size droplet, you will be able to see that oxidation progressing between this one is, I believe, potassium chromate to vitamin C drop. Something that students just put together. Complexation reaction, simply general chemistry. Copper sulfate with ammonia, making complex reaction, things like that nature, depending on how much ammonia is replacing. And is it copper hydroxide or copper nitrate and things, copper ammonia complex. Depending on that, the product is soluble and insoluble. This is general chemistry. This is something you don't come up with it purposely, but while you're doing the experiment, naturally extended. We were interested in biomineral. We wanted to know calcium carbonate has so many different polymers, but can I control this polymer using soft template? But students need to learn about precipitation reaction in general chemistry anyway. They have to learn calcium carbonate is insoluble. That's sometimes in general chemistry you get things like that. So one of the droplets is calcium chloride. The other one is sodium carbonate. You bring it together, you will be able to see from beginning to ending, from the birth of the precipitate to the finalized crystal. You have so many concepts you can teach. Only one of those 5-minute video. On the saturation, surface saturation, precipitation, solubility, crystal structure, polymorphism. So many things you can talk about. You have to think of it that way. That way, you will be able to do the research at the same time. You will enhance your teaching, and you will make it as an education paper. And one day you will make the JAX paper as well. That's how you have to always think about that, not two separate things. So I'm going to more now focus on what maybe you came for. That is, I'm going to tell you a little bit about project stability. So you already get this idea that I put it together, so this slide does not need any introduction. I call myself as a somewhat chemistry, material chemistry. So when you think of material science 101, what do you think of? There is always something that is composition, structure, property, and performance. That's what everyone material science 101 all the time. So I think of that as if I put together as a team, start with the composition that is individual group member, and how I put together, knowing who they are, and then as a result of that, as a group, we perform. And we have characteristics, and as a result of that, professionally we grow together. So each one of them, I'm going to tell you how I do it, and I welcome any interruption or questions from this point on. I start recruitment from first year. I started my career at Iona 2004, and since then I never skipped a single year for teaching general chemistry. If I skip 1 year, that meant that I do not have a student that year. That means the entire year I'm starved, basically. 1 year, a whole gap. General chemistry, as I just mentioned, there are so many concepts that you can bring your research in. You can sneak in while you're talking about concentration, molarity, osmotic pressure. There are so many ways you can actually bring your research in and then introduce them what you do without digress too much from the general curriculum. My building is called Cornelia. This is the exact slide that I put it in one of the first lecture that I do. So I give them something like this and then say, this is Alice in Wonderland. Behind the curtain, there might be something wonderful. This is where my lab is located. This is the building where you are looking at it, and you're sitting right now. So please discover what's behind that. Now, sadly, I hope that there are 100 people line up the door, but my class usually have about 40 students in my class, and I was told that from next year, I'm going to have to shrink the class even further, so the maximum number is now 25. So I can't even have more than 20. That's not good news for me, because I want more. But this is the student to see it in the first day of a lecture, and I talk about some of those. Okay. So, and I gave that invitation to everybody to come. Unlike the University of Michigan, it's a small school, and there is one science building, so they know where to go. If I say room 12, there is only one room that holds 12. So they're gonna come, and a few of them stop by, and that's how we start to have a conversation. During the first semester, I get to meet students. What I do is I usually invite them for lunch. I have to eat lunch anyway, so it's not like I set aside a different time. So I call 5 people. I can't engage so many people at once. So 5 people I call for lunch. And another 5 people I call for breakfast, coffee. Who's a coffee drinker? Okay. So I get to know, for second week, I know pretty much everybody. It's a 40 students, like 800. So it's not that difficult. And by then I have everybody on my cell phone as well. They don't mind. They usually give data just to anybody. They are trained in this generation to give up their data. So they do that. So I not only try to recruit students to be my research students, that's the second. The first is I want to train them to be a serious student. Whether they are becoming a chemist or biologist or whatever they want to become, I want serious students and their attitude to be there. So I have their cell phone number and everything, so that if they don't show up 5 minutes later, I text them. Things like that nature, and many of them responded to that kind of a personal interaction. And having those small group meetings, I continuously do that from the first semester. I get to know them, and then they get to know me. And no matter how much time I induce us to talk about research, just to some students are not turned on, then that's that. And out of those, I see 3 or 4 shows a strong interest. And then the end of the semester, and then the winter session begins. I don't know here, but at Iona, there the January, 3rd week of January, spring semester already begun. So we have very short winter break. But first 2 weeks of January, there is a January winter session that some of students can take classes. I make a class called Introduction to Chemistry Research. And then I open just for freshman students who's interested in my research. It's 1 credit course, yes, you have to pay for it, but you're gonna have to be serious about it if you wanna go into that. Now, for that 1 credit, I give 2 weeks of my time for them. So during that 1 week January intercession class, I meet them 8 o'clock in the morning until 5 o'clock in the afternoon together. They have, for the first time, experience what it is like to be in a lab all day and without having to go outside. Which we all experience, right? During that time, I also talk about safety things, all the other things. As you see, my research is not something someone who just walked in, oh, can I do research here? I'm going to start doing that. It's not working out that way because these micropipette requires training. You know, all these things are non-conventional technique that I have to train extensively before I can trust them. Otherwise, now you go $12,000 bills and I can't kick them out just like that. So I don't want to have them that traumatic experience. You teach you about ethics and all the things that you learn in graduate school. I do that freshman year winter break for 2 weeks. There are always 4 or 5 students to sign up their class. Some I invite them to sign up, and they have a choice not to do so. And those students are going to be future research group members for my meaning for past 10 years. That's what I do every winter. Now, once you have a student, what do you do with the freshman? Now, at the moment, I have done this many years. I have sophomore, junior, and senior. However, at some point, you start something, and you have only freshmen. Now, when I first studied, obviously, I didn't have this kind of luxury. I have 1 student, so I take her everywhere I go, and she learns everything from me. Everything from I use my chopstick to drink coffee and everything. Believe me, when you have undergraduate video, you have to be very careful about what you do. How you weigh things, how you take out certain things, how you wash your hands. They want to see, and they think that's the way to do it. And then later you realize, oh, what have I done? So once you have this group of students, finding a team is very important. Just like you and me, we don't do well alone in isolation. You want them to create an environment where they feel comfortable. After all, research is not fun all the time. So you have to make it fun without diluting the content of it. So you have to know your students, what they like, what are their tendencies. Are they a morning person? Are they sleeping after 2 o'clock? Everything you need to know, what kind of movie they like, all that kind of thing. That will help you create a team. Now, I assume that at this point you already have some other students, so that's why I mentioned about this creating a team. Once you go through the first year, next year you will have already first sophomore and then freshman, so you can think of the creating a team. You can pair with the athletic student who has often practice in the morning. So the timing is similar, their hobby is similar, maybe they are from the same region, they went to the same high school. You know, they're vegan, you know, whatever you can think of. You will find a good match with that student to someone else who's been there. So I create this mentor-mentee. This is not the same as a research project. At this point, I'm not talking about research project. I'm just talking about just a social network, so that they have a reason why they come back. the lab, even though they do nothing but homework in the lab. And it is okay, they can do that. So that will create tight-knit community. Sometimes they don't even come to me to ask about what courses they have to take next semester. They talk to with each other. Oh, so-and-so said I should take all these series of things like that. So they become more than a mentor, almost like a life coach. They really become. So you create that, particularly in their freshman year. Once that's done, now you have to seriously think about research, because it's not about social gathering. You seriously not getting it. So as I mentioned in the previous couple of slides about the nature of my research, this is the current project that I'm running. How many of them? 1, 2, 3, 4, 5, 6, 7. There are 7 days a week, so that's perfect. And the 7 numbers I can manage. So these are different types of projects that is currently running, and 2 students are within each project. I put it into certain category of the field, although one could doubt that it's not just biology or biophysics, but I put it this way. The reason I put it this way is because the student interests differ, and student major actually differ. Not all my students are chemistry major. In fact, 2 of my students are computer science major, 1 is a physics major. And they bring different things to the table. All they have in common, they know the value of chemistry. They know they wanted to connect the chemistry to what they do. That's what they have in common. So, for example, a student who was a physics major could go into biophysics. So membrane capacitance experiment is carried by that student with another student who is doing physics as a minor. We have an education program, I earlier mentioned that. The student who wanted to go into art and education, they are the ones who come up with the series logo and things like that nature. And all the programs that we use to analyze all the data actually involve a serious calculation. To do that, we do not use any commercially available software. There is none to use that specific purpose. Our students developed that program, and then we use that. In that sense, we cannot survive without one team not doing their job, because then I have to analyze 10 hours. But if that guy created the software properly, then I only done in half an hour. So we rely on each other, but they also use their strengths to contribute, and they get the satisfaction they all share in the end of that. Now having that structure of a project is also considered based on what kind of a team you have. You may not have a computer science major in that certain year, then forget about, developing certain software, things like that. No one else in my group ever wanted to do anything like that, then you come up with something else based on what they're good at. You always, the focus is what you have, not what you wish to have. And based on that, you will be able to make anything out of it. So I usually put 2 people. 2 people in a kitchen is doable, but not 3. So 2 students always work together. It has to be always a lower classman and upperclassman, so that one person graduates, then that person becomes the leader of that team. So we have some level of continuity, although that happens to be always an issue for doing a research in PUI, but I managed to do that. I believe this can be done. When they seriously sign up after their freshman year, before they start the summer, I have them sign the contract. So I do not show you all the contract language, which sometimes is a little scary, but the highlight of the contract is something like that. Project Symphony members take responsibility, and then underneath it's long sentence of 300 words of what that means. Thou shalt not steal or relocate this stuff or things like that nature is all there. So they learn to behave like a serious graduate student. They learn everything. They are freshmen, but they should start with that. They should be respectful to others, so you don't just leave stuff on the bench and then have the next person suffer. They should have patience and different set of priorities. Sometimes students ask what does that mean, so I simply say, well, that means that Friday night you don't go for a movie, but rather start working. Oh, okay. Can I bring my video here? While I'm doing experiment, can I watch the movie, which we do all the time? And there are a few slides after that. There is a lab panorama videotape, and there is a huge screen in the lab that is connected to the microscope. So it's not designed for movie, ideally. It's designed for whatever is happening in the microscope slide is actually showing. Because I was using it for the classroom demonstration, but somebody disconnected that and then I put it into their laptop and then and they are always thinking, undergraduate students are not convenient pair of hands. Who's going to come make the job for you? Or who's going to just wash the plate? If that concept is there, you might not have wasted your time. They can do it. Students can always reach out if you set the standard high enough. They will stop right there. If you say this is good enough, they will stop right there. You have to continue raise the bar. Eventually, they become thinking like independent researcher, and that's clearly possible. Yes.
With that contract that you have signed, do you also outline what they can expect from you?
Yes. That contract includes all of those things. This contract is always mutual. I hope I have a chance to talk about those things later, question and answer. So hopefully my explanation doesn't scare you too much. Then you're going to think that, okay, I don't have a mutual break. I'm about to say you don't have a summer break either, so what do I have? I don't have a Friday. I don't have a snow day. What is happening here? That can happen, but it all depends on how you feel. If it is fun, then probably don't mind. So let's imagine that these students have gone through that freshman year and then first summer. And these freshmen who went through that winter-January intersection and then have been paired with the mentor-mentee relationship actually need to stay with me 10 weeks of summer. And that's in the contract. If you just cannot do it, then okay, so you cannot be involved in this because it involves serious commitment. So during the 10th week in January, summer is 3 months, so you have 1 month. My office is the second floor, my lab is the first floor, and then I go to the lab 8 o'clock in the morning, and then I leave from the lab at the end of the day whenever that might be. I never set a foot to my office during that 10 weeks. I'm there. Sometimes the students are there before me. I eat breakfast with them, I eat lunch with them, I eat dinner with them if we have to stay here till dinner time. In the meantime, we can have a break for yoga outside, or we watch a video, or we go out for a movie. All of those things, normal life, with 50 people together. And each group, each 2 students have their own independent research to carry out. I'm there all day. Why they do? That doesn't mean that I am over their shoulder, like, what did you how did you see what? I don't do that, but my presence is there, so they know I'm there doing something else. Hopefully I'll tell you a few more things after I go through a few things because time is running up. As I mentioned, I sent my students to Japan, so this one shows the PJ, who is current lab captain, was in 2 weeks, 4 weeks in Japan this summer. As you know, the time is 12-hour difference. So by the time he goes to sleep, it's by the time he's starting to do, and every day he would Skype in, we say hello to him, he say hello to us, then he talk about what he has done and check out. And the next day, we did that every single day for 4 weeks. He checked in willingly, not because you must do this, but rather he wanted to see, like, oh, I want to see my group member, my sisters and brothers, and then they talk about it. And while he was there, actually, he had his 21st year birthday. And he sang happy birthday over Skype. Okay, now, very, very different story during the academic year. As you know, undergraduate takes 18 credits, or sometimes the challenging one even wanted to take more. So therefore, amount of work you can possibly get it done during the academic year is a small fraction of what you have achieved during the summertime. Me saying that is a very different story that they have experienced. Now they have gone through the summertime. Usually that's the time that I plant seed, meaning that all the data that I can possibly write a paper is done over the summer. I don't have time to write a paper over the summer. I have to collect the data every single day. Every single day I have to look over 7 different projects and then give them a guidance on what we have to do next day. So that next day is not wasted because I have only 10 weeks in a year. And then after summer is done, then in the fall semester, I know research is not moving that much, so therefore I can look over and then start to write a paper. So during the academic year, do you just park your car in a garage? You can't do that, you have to keep going on. So all these different projects is spread out to Monday, Tuesday, Wednesday, Thursday, Friday. And next slide give you a little bit of flavor of that. Individual projects is still going on. Individual pair of a team, they form together over the summer, still going on. Each one of them, they analyze, they carry out experiment. Each team meets with me every week. And then in the meantime, we do not have a lab manager, no other things like that. I'm going to be pretty much busy going into classroom all the time. So we need someone who's in charge a little bit. Some chemical delivery, while putting it properly, waste disposal, all these things. So senior student to becoming a captain all the time. So captain is organizing certain event, and then group meeting happening just like a graduate school, but not so frequently. So it's lucky if it happens once in a month. It's not like every week you do that. There's nothing much to discuss, so things are not happening that much. So eventual goal is presenting and writing a paper like this. So I just thought that would be interesting for you to look at it. This is actually my calendar for this semester. So these are the research schedule for Monday to Friday. And as you see, 2 students are paired. As you notice that the color, this different color matching is one day in a week is a preparation meeting, and one day is actually study day. So basically what this means is students work only once in a week. And that's also quite a lot to ask when they take organic chemistry, physical chemistry, things like that. Even though they have a 5-hour block, probably, doing the research is not the first thing on their agenda unless they are really, really motivated. I have a PChem exam, organic exam all the time. So therefore, I can't ask more than 1 week to show up in the lab and do the research. But they are always around. They may not do the research, but they are always around. However, I want them to do the meaningful work, spend the meaningful time. So therefore, I need to know what they're doing. So I meet with them before, so that we discuss about the result, and then we plan about what experiment they do, so that they can spend whatever amount of time in a meaningful way. So you will see that each team has 2 days allocated to it. And calendar is packed. Yes, I will be busy all throughout the week, but this is happiness in a way that everybody comes in, oh, this is data what I have, so what should we do next week? So let's think about it, things like that. All the way underneath is a freshman shadow. So these are freshmen who does not have a project, but the student who is very much interested in from freshman classes. So they are invited to each one of the days that they can afford it to, so they can spend a great deal of time. So they can watch what you're doing and then pick up whatever they can. If you count all the number of students, and then you can see that you can kind of manage 50. I don't know, I can do more than that unless there are more than 7 days a week. But that's pretty much what I have been doing. I always emphasize that, yes, somebody has to manage the whole thing. But I like the idea that a faculty as a leader, meaning walking alongside with them, just to make sure they don't trip over or they don't go to the wrong direction and waste a whole different set of amount of time. Not so much in micromanaging. I think that's the same story, and the reason that perhaps I have this skills, what I do now, is because what I learned from my advisor. Not like micromanaging, like what are you doing now? What are you doing tomorrow? Not like that. Nobody like that. Same thing applied to undergraduate as well. You have to give enough room, but yet provide certain boundaries. So I always think of that as, yes, the leader is a wonderful concept, but undergraduate need to be managed, but don't over-manage. Clearly, this alone will take another many hours. What do you mean? How do we do that kind of thing? Outcome is clear. Outcome is basically what we achieve. Do we just doodle around and then spend thousands of dollars of chemicals? Or do we contribute to some new scientific knowledge and be proud? And we actually do. So I this sounds a little corny to draw the graph and how wonderful our achievement is, but this is a reality. The number of students that I worked with, a number of students who actually published or presented in a professional conference setting number is clearly, you can see, on the rising. I try to give them as much opportunities to go out there, meet other chemists, so that you see how much big world is out there. What you know is a fraction of a minuscule portion of it. Surface and colloid chemistry is wonderful, but there are a whole array of science out there. They have to experience it. So taking them to a conference is my first priority. In fact, the reward they get at the end of summer, yes, I pay them over the summer, last couple of years, thanks to your taxpayers' money, that is NSF. However, there are many years prior that I don't have to pay anything. They do not want the money. Money is not an issue. The experience is all they want. And at the end of that, at least, I found a way to somewhat, scramble for money so that we can take them to a conference. ACS National Conference is always our highlight at the end of the summer. So every year I take them to the conference. This is the most recent Boston conference, like two, I think there was 15 of them. One of them could not take long travel. So in the end, what we care is about their future beyond undergraduate. Not so much how many papers you have or how many publications. That's a small reward. I want them to be a good, intelligent citizen, understanding science, particularly appreciating chemical science. I am proud to say for everyone who's involved in this endeavor, although they may not become a serious research scientist, 100% stay in science. Nobody turning into something else, other non-science related. They all retain high GPA. Somebody may say that, oh, it's selective because you recruited a good student to begin with. That's not true. They were not a good student to begin with, not necessarily all the time, 50-50. But they still remain a high GPA. They have additional drive that they didn't know they had it before. And the postgraduate record is pretty much speaking clearly. Many students at Iona College are first generation of college-bound students. If you go to PUI, depending on what it is, chances are you will see many of those population. They do not know there are something else beyond the bachelor's degree. Like, what do you mean after 4 years? I go to school again? What's PhD? I don't tell them what PhD is. But for those students, 4 years later, so what are you planning to do? Oh, of course I'm going to a PhD program, I'm applying to that. But that's the moment you get all the reward for Saturdays and snow days and winter break and summer break. You forget about it. Because these students, altogether, I add up the number, 30 of them, 20 of them, 10 is in PhD program, 10 is in medical school. The 6 of them is either teaching or master's level and got a job. 4 of them doing different kinds of entrepreneurial work. And when I think of those things, those are the students who does not have a brother and sisters or doctors. Parents went to college, they already know what their future holds. My mother told me that I have to be. No, none of those. They are the first one. I know everybody in their family. Their parents come to me talking about how their life has changed because of this. I'm not saying PhD is the best thing you do in your life, but if that's what you chose, that's a darn good thing that if you decided to do so. Particularly for people who never knew about anything beyond that. That's what you are capable of doing. If you become a teacher in the PUI, deeply involved in students in a personal level. And I'm not saying this is a perfect recipe you should follow. You will come up with a different recipe. Maybe it's even better and things like that. You can actually change that person and then their friend and their family and all different generations. So I think that's quite a unique, rewarding experience. Now, my research lab is that limited the number of students, but as a result of that, the side effect happens to be I am currently the chair of the chemistry department. When I first joined chemistry, this is sometime over here. This is the entire cohort with 9. And my class, instrumentation class, there were 3 students. Things like that. They can't offer class every year because there are not many students, so you have to wait another year. So that the critical number has been added together and things like that. So look, what this you can't lie about the number. Number actually tells you something about it. Is that not all of them is my students? Obviously, as of now, 15 is my student. So it's a quite a percentage, but the rest of them is a chemistry major. Why are they chemistry major all of a sudden? Was it some people around the New York area interested in chemical science? The population we recruit to our students from hasn't changed for years. And they see what's happening. They just drawn to it. I just want to be with the people who is doing more and do the challenging for the fun of it. So as a result of that, we were able to bring the level up to this much. Obviously, many things involve money, and I hate to put this kind of a business talk, but sometimes in academia you have to do things that doesn't necessarily agree with your heart. So return on investment is what people care a lot, and clearly the more money you have, the more toy you can buy, the more toy you have, you can please more people. You don't hand out cash so that they can do research. That's not how it works, but you can hand out toys. And you can take them to places that they haven't never experienced before. So money wouldn't hurt. So you can see that there is a strong correlation there. All throughout my career, all the things that I briefly packed together within, I think I did it exactly an hour because we studied in 20 minutes, 2 more minutes. That I was blessed with getting all kinds of support. And actually, Mark was the one who told me that I should apply for PRF grant. Remember that? That's my first grant. I took his advice and I applied for that. I got that one. That was $25,000 10 years ago. It needs a lot more right now, but back then, that was the first grant that I can buy my microscope or my micropipette, and I can recruit one student because now I have to work. And then that led to realize that you just saw that seeing is believing, those chemical reactions happening in a microdroplet, purely educational, emphasizing the conceptual understanding and things like that. That was actually educational grant. It was funded by Dreyfus Foundation. And that was quite competitive grant. I was able to connect that. Did I stop my research to do that, to impress people in education? No, it was a natural extension of what I do, and we did find that as well. Since then, I've been blessed with a grant, so I've been continuing receiving NSF grant, and that's also thanks to all of us believing in sciences and its impact for that one. But most thankfully, because of a wonderful student of mine. I always say that whenever there is a symphony, there is a conductor. The conductor actually doesn't do anything. They don't make a sound, but they make it on the cover of the CD, and I think the most important person. So I always take the credit. I get to be invited to like these places, talk to these wonderful people. I go around to places and brag about it. But actually, people who make a wonderful sound are these folks, and they are the one they consider it as a family member. And the people who graduated 5 years, 6 years, 10 years ago, they come back and then look after each other. And then they find that they are next path and things like that. So you can do the same thing using some of the things that I shared with you. And you can have a wonderful career as a superior research scientist, as a chemistry professor at the same time. Really visually touching students that you're working with. You can make a really high-profile research laboratory with 100% undergraduate students. For that, I say PUI stands for pure, not primarily or predominantly undergraduate institution. With that, I'm going to end my demo, and I will open for your questions.